Okay, so let's start today. And this is going to be the last lecture on corner methods. And what we're gonna cover today, so still chapter 6, corner methods. So we will cover something that I think you may encounter quite often, because I encountered it before when I didn't really know corner method that much. The first thing that we will study is in the textbook, we say Approximate Corner Feature Map. I don't know whether this is exactly that word that often used here, but it may be. And then there's some keywords that you might encounter quite often is random free feature. So this is, one of the common way to approximate kernels if we want to use kernels in practice. And also it carries, some idea about how one design an approximation in the area of machine learning. So, in different area of computer science, for instance, programming languages, when they design approximation, the kind of criteria they are using is a bit different from what you will encounter today. So that's one thing that we're gonna cover. The other thing is something called negative definite. It's called negative definite symmetry corner. So, this gives a kind of another idea about how to, it gives us some idea on how to design a kernel. So we said, when we design a kernel, the intuition behind the kernel function K is to compare similarity between two inputs. And then most of our derivation or formalizations and some guiding principle of designing a new kernel came from this shape, which is essentially it's an inner product over some rich feature space. Okay? So that was how we design a kernel. But there's another intuition. The other intuition is use the distance between two inputs. So if we have X and Y, if you somehow compute the distance between X and X prime in some feature space, this also provide a notion of similarity measure. If two things are very, very similar, their distance will become quite small. If they are very different, their distance can be very, very large. So this gives another formal way of capturing the idea of similarity. Then the question becomes, can you somehow design a kernels out of this notion of distance? Or is there any, just like a kernel has, some indirect way of saying it's essentially an inner product. So positive definiteness and symmetry property, they ensures it's an inner product over some big feature space. Is there any way to say that we have a binary functions and that binary function is essentially computing the distance? And it turns out there's a possibility that's called a negative definite symmetry kernel. And it's also closely related to the PDS kernel that we talked about so far. So that's another topic that we're going to talk about. And they will give you some idea about how, one of the most popular kernels that you will encounter in practice is the RBF kernel that we talked many times. So this is sigma square. And then the idea of negative definite symmetric corners will enable you to generalize this notion to more general context, to be more general context. Okay, so let's start with the approximate corner feature map. So the algorithm that's based on the corners are pretty good so for instance, although we are not talking about this, there are algorithms so-called based on so-called Gaussian processes. They can be expressed in terms of corners. Also, the corner version of support vector machines, that also work pretty well. But then but there's one big catch behind of these type of kernelized algorithms. So what are the big issue of kernelized algorithm? So the one big issue behind this kernelized algorithm is that these algorithms works by essentially remembering the samples in the training set. Okay, examples in our terminology, it works by it remembers, it solves some optimization problem, but the process of solving optimization problem involves really touching all the examples many times. So, and often it requires not all the examples, of course, but the problem is that when you compute an optimization, it has to consider pair of all the examples. So if we have that's because it has to compute inner products between xi and xj. So if we have an iterative algorithm to solve optimization involved in the learning, each step of the optimization has to compute the inner products between any two elements in the sample or in the training set. That means if our size of the sample is m, so there are m examples in the sample, then each step of the optimization will take order of m squared, which can be very, very expensive. So if our sample is very large, so it has, say, 1 million examples, then 1 million square is a really large number. Okay, so the problem I want to talk about is there's a computational problem. So optimization can be quite expensive. And perhaps a bit more important is that now, if we solve the optimization, in other words, we completed the learning process and we learned something. And if you remember the support vector machine, there's a function x, and then a function is defined a certain way, but one of the things that function does is, it was written like this. So it has to compute inner products between the new input x and the examples from, the examples in the sample. And if there are a million examples, to make a single prediction, we need to compute 1 million steps, which may be too expensive. Okay. So this algorithm is great. It has many guarantees and so on. But this may be also quite expensive, at least order of it. So the algorithm is great, but in practice, if the size of the sample is very large, it can be very expensive computationally. Okay. So what we want to do is that we want to enjoy many benefits of the kernel, because for instance, RBF kernel is essentially considering all the polynomial features of the inputs and so on. So we want to enjoy many benefits of the kernel. At the same time, we want to reduce the computational complexity. Okay, so then one approach. So what is the core? So one approach to do so is to make the feature space explicit. And then in some sense works on the primal form. So what that means is we make feature space explicit. We have a feature map V that takes inputs to some space and maybe, but in our solution for this computational complexity problem, n is always finite. And then instead of, if you remember the support vector machine, really this formula came from the fact that weights were the slope of a linear function that we compute is of this form, ai star, yi, xi. And then what you see here is really just computing the inner products between W and the input X. Okay, but instead of just remembering W, we indirectly express the use of W in terms of inner product. That's great because it allows us to use infinite dimensional space and so on. But on the other hand, if we care more, if the size of the sample is very large, that can be very expensive because, as I said, the complexity of computing this is order of m, and if m is very large, that can be, it can be intolerable. Now, so the idea is working on the primary form is really directly computing W. So we want to compute this guy. And then express f of x in terms of W directly. So then if n is not very large, okay, if the n here is not very large, then in a sense W can be represented compactly. So if n is say 20, then the computational complexity involved in computing f of x is going to be just the addition, multiplication of two real numbers and addition of 20 20 real numbers, which will be much cheaper than computing like a million step in the dual form. Okay, so that's the idea. So when you have kernels, we want to, in a sense, represent the feature space of the kernels directly, and then make sure that the feature space is small and we have encoding, and then we directly work on the primary form. Okay, so that's the idea. But the problem is if you want to do so, we need to approximate. So if you have an original k, but if you do like this way, then k of x and x prime is not going to be the same as inner products of v of x and v of x prime, because we want to keep n small. So n is not really the one from the RKHS. It's just something that we choose. Okay. So it's going to be not exactly the same, only approximately the same. Okay. Then so we want to ensure, although it's approximately the same, it has nice guarantee. So nice justifications about the relationship between k and this newly induced the quantity that I'm describing here. Now let me mention one more thing. So that we talked about last time, empirical corner. So remember the word. Yeah, empirical corner. This is not quite a solution here. I mean, it ensures that it follows the same kind of plan. So the empirical corner case, it allows us to define this feature map V, and it's finite. And then there's some approximation relationship between the K and the inner products that we are computing using this V. But the problem with this definition was something which is not very satisfactory from our perspective here, is that n is equal to, in this case, is equal to m. Okay, so that's not what we want. If n is equal to m, that means, essentially we are not saving anything in terms of computational complexity. What we really want is, we want to have n that is significantly smaller than n. Okay, so that's what we want. So the question becomes, how can we design this in a principled way? And then approximate corner feature map provides us a solution for this. So what is approximate feature map? An approximate feature map is based on the following theorem. It's called, I think, Faulkner's theorem. So that says, the textbook is written as theorem 6.24. This theorem says the following. It says that if we have a k kernels, which is a binary function on R, and then this is a symmetry. Let's write down. K is a symmetry. And in fact, we know the form of K a little bit, which is that K of x and x prime is defined by some function g applied to the difference between x and x prime. By the way, we are assuming x is equal to some Euclidean space, finite dimensional Euclidean space Rn. So we can compute the difference and g can be applied here for some g, which is a mapping from Rn to R, but such that G satisfies like two properties. One is G is continuous. And the second property is that G of 0 is equal to 1. So this is a bit like saying it's properly normalized. So these are the setting. And then there are some typical examples. This RBF kernel satisfies this type of relationship. So in that case, then in order for K to be the kind of kernel that we want, it has to satisfy one more property, which is positive definiteness. So P is positive definite. If and only if the following is true, there exists in G. So if it's a positive definite, if and only if G have some property, G is the Fourier transform of a probability distribution. P on X. So what does this mean? This means that the G of X can be computed like this as an integral. So it's an X, but same as R of N. the integral over n, but we are computing exponentiation of the, complex number I inner products of W and X. And we can write it like a P of T dW, which means that we are computing the integration with respect P of W. But if you're familiar, if this makes you confused, you just think of the probability distribution, which have a density, then this is same as P of W dW. So P can be probability measure, then it's the one that you see on the top. If you don't understand what I'm talking about, it's really just a Fourier transform of the probability measure P of W, probability density P of W. Also, if you're familiar with probability theory, you can see that this is a characteristic function of P of W. Okay. So then this one, what does that tell us? This tells us that if K is of this form, K is essentially defined in terms of a difference between the two inputs, X and X prime, and then there's some transformation afterwards. So then the positive definiteness of K is related to the form of G, and then the G has to be Fourier transform of the probability distribution, some probability distribution P. Something that's more useful for us is to express this Fourier transform a bit more directly in terms of the following. So for instance, if K is positive definite, so if K is a positive definite, then it's a Fourier transform. Okay. But the way we're gonna use this result is this direction. Let's just write it this way. This is the important direction for us. Because that's the direction we're going to use to derive an approximate corners from K, given K. So now how we do it, and the way we do it is to express G of X slightly different form. Okay. So what does that tell us is that it's really saying we are computing the expectation of P of W. And then, this is an integral, something that you see here is an exponential over I. So this is really, if you remember what you learned in the perhaps the high school, this is same as saying, choose a red color, same as saying, I think cosine of I WX plus sine, no, I, not I, cosine of this guy, and then sine of WX and complex number. But because G is a real valued functions, if K is positive definite, this theorem implies that the G of this second term, the integral of this term has to be 0. So what this will tell us is that G will have the following form. The form is, it's an expectation of cosine WX. So that's what the theorem really tells us. If K is positive definite, then G should have the form that I just wrote in below. Okay. So why that form is useful? Then G can be approximated. This can be approximated in terms of samples. So in the machine learning, especially if you work on something involve more probabilistic approaches. So I mean, uses the probabilistic approach. I mean, this type of idea appears quite often. If you went the process of designing an approximate algorithm is to express something in terms of expectation. And after expressing something in terms of expectations, we approximate it by sample average. So to approximate this guy, what we can do is we just sample L of W1 to WA generate independent samples. IID means that independent samples from P. And then for each sample, we just compute the terms inside the expectation. Then take their average. Cosine of W, I, and S. And I mean, this is very nice for two reasons. First, most of the time by so-called strong log large number, if n goes to the infinity, the term that I just wrote converges with probability 1 to g of x. So that's one good thing about it. The other good thing about this is that it's so-called unbiased estimator. So if you take the expectations on the right-hand side with respect to these samples, so then on average, in other words, in expectations, that becomes exactly the same as g of x. Okay. So that's the kind of, so this form, although looks very mathematical, it actually leads us to derive an algorithm in this way. Now, so then the situation arises often, and it turns out that is the case. So let me give you some examples of K that is of the form, some function G applied to x minus x prime, and then corresponding probability distribution P. Okay. By the way, the kernel K, which is of this form, is sometimes called translation invariant kernel. That's because if you translate to inputs x and x prime by some quantity, I mean, because we are taking subtractions, we are subtract these two, I mean, the one term from the other, this translation doesn't make any change at all. It just cancel. Okay. So this is something called translation invariant kernels, and that appears quite often. And for that kernels, we cannot have this form. So what are the examples of K and P? So here are some examples. So the first example is RBF kernel. And the definition of the kernel is, I mean, the simplest case is that it's a K of x and x prime exponentiation of x minus x prime square. Okay. So then we may ask, what is corresponding P? So then, I mean, here x lives in space R to the n. And what is corresponding P? P has to be a probability distribution on R to the n. So it's a distribution on R to the n. It turns out in this case, it has a so-called density, and it really becomes a normal distribution. So it is 1 over standard normal distribution, 2 pi dimension n divided by 2, and then exponentiations. Let's use W because that's the symbol that we used. Exponentiation of minus 2 W squared. So it's a normal distribution, which maybe some of you are familiar with. And And then for the other example, I want to talk about two other examples which appears in the textbook. The one is Laplacian corner. So where the corner K is defined very similar to the RBF corner, except that we are instead of using the L2 norm, so we are using L1 norm. So that we take a difference between x and x prime, but we take a L1 distance. This means summation of for all the coordinates, we take the difference between x and x prime, and we just add all of them together. So that's what this L1 norm means. And what's the difference? I mean, if you compare the one above and the one below, I mean, they are really saying if x and x prime are far away, the value will be very far away. The value will be very low. If they are close, essentially, if they are the same, the value will become 1. Okay, because if x and x prime are the same, it's 0. Then the term that's inside the exponentiations becomes 0, so that will become 1. So starting from 1, if x and x primes go far apart, then the value will decrease. But the one above using the quadratic term, the one below use a linear term. So the rate of decay, so when x and x primes are becomes far apart, the rate of decay in Kn, this RBF corner and the Laplacian corners are different. RBF corner decays much faster because it decays like square of exponentiations. Laplacian corner case, it decays a bit slower because it's just just linear terms with an exponentiation of the linear term. Okay, so the slower decay. So it means that when x and x prime are far apart, RBF corner will give a smaller number. Okay. So for that, we may ask what's going to be the corresponding probability distribution. And the probability distribution in this case turned out to be a Cauchy distribution. So it's independent Cauchy. So we have some products and products, and 1 over pi wi squared. So it's a Cauchy distribution. This is one of the typical heavy-tailed distributions. So the Gaussian distributions that you see in number 1, its tail, it's the probability of having very large values really low because of it decays the square exponential rate. But this P of W, the Cauchy distribution case, it decays in the polynomial rate, so that there are more chances of having very large values. And the third is this is actually Cauchy corner. In this case, it decays even slower than the Laplacian corner, and it's defined a very similar way to the Cauchy distribution. It's 2, 1 plus x I minus xi prime square. And this is even slower when the xi and x prime, x and x primes get far apart, that the number becomes smaller but much slower rate than the Laplacian corner. And in this case, the probability distribution turned out to be Laplace distribution. So it's somehow like Laplacian and the Cauchy, they are dual with each other. So So these are the examples. And then now the question becomes how we can use that result to design an approximate corner. So here's a way to do it. So suppose we have K and G and P from Faulkner's theorem. And then design of approximate corner is exactly what I told you before. So when you want to approximate the corner here, here's what we do. So we first sample omega 1 up to omega L from P independently. Then we define. So this is a sampled once and for all. And then define a new corner, K prime, as an average. And then what we are doing is that we compute the inner products, and then the inner products of cosine W1, Wi. So inner products of two vectors of dimension 2. So we have one vector and another vector of dimension 2 and compute their inner products. And the first it uses x, the second uses x prime. Then both defined like this for cosine Wi x and sine Wi and x. And also cosine Wi x prime sine Wi and x prime. So what's really going on here? What's going on here is that really what happened is we sample from the sample W1 to WL, we are generating two L features. Okay, one feature is for each of the Wi, we have a cosine Wi blank, so that's a one feature. Sine Wi blank, that's another. The other feature for Wi, and because we have L many Wi's, so we will have a 2L features generated from these samples. And we can see that these Wi's are random. This is really a random features, okay, randomly generated feature. So the K prime is also random. But once Wi's are all generated, features that becomes fixed, and then we are just using those features to define K prime. And this is the kernels, because the constant doesn't matter. We learned that the summation preserves the kernels, and also we are defining it in terms of inner products. Inner product is whatever you do. Whenever you define something in terms of inner product, it always become a kernel. So this is a kernel. So then that it is a kernel, and although the Don didn't express this explicitly, this kernel is really defines over in the feature space R to the 2L. Okay, I said there are 2L features coming from each Wi's, and so it's defined like R to 2L. So if we want to use a feature space of a small size, if you choose some small L, that will give a feature space of small size. Of course, then approximation become large, but this type of construction gives us a control. So then the question becomes, how good this approximation is. So then that's what we can prove in the next theorem. I think it's proposition 6.25, and that proposition said, yeah, what we got is quite okay. So it's what it tells us is on expectation, this k prime of x prime same as k x prime for x and x prime. So I mean, so they mean this expectation is over for fixed x and x prime. We can compute the k prime, the one that I just told you for, and then we compute an average with respect to all the samples. Okay. And then compare that value with the original value k, x, and x prime. And then it turns out they are the same. And the proof is quite simple. So this means our k prime is an unbiased estimate of k. Okay. Why this is the case? I mean, it's sufficient to show so only the case when L is equal to 1 because of the linearity of the expectation. For L is equal to 1. Okay. Then you can use linearity and then derive what's claimed in the proposition. And actually the form of the proposition is for the case when L is equal to 1. So then when L is equal to 1, what's going on? So we have this term, W descending from P. And then we have an inner product, cosine of Wx and sine of Wx, and the inner product cosine of Wx prime and sine of Wx prime. Any expectation of this guy. So that's the term, this term. So then this expectation, I mean, if you just unpack the definitions, W, it's just cosine Wx cosine Wx prime minus sine Wx sine Wx prime. But by some simple equation on the sine and cosine, I mean this the term multiplying two cosines and then subtracting multiplication of two sines with the same parameter is the same as cosine of the Wx minus Wnx prime. This is the simple equality, I mean some well-known form by the well-known formula between on sines and cosines. And then this one, if we now use an expectation, can be written as this sine of W x minus x prime. And perhaps you forgot it now, but this is exactly the formula that I told you. What is this? This is the integration, so up to the n of the real part of this exponentiation function. And we integrate with respect to p. So if you know, just be more exactly, well, you can think of this as p of w dw. And by Bochner's theorem, that is the same as G, not X. Have X minus X prime. By Bochner's theorem, this is the same as X minus X prime. And that is exactly the value of the kernel K X comma X prime. So this shows that what we compute, our our approximate kernel based on this random Fourier feature that is on average compute the right value. And so it provides a justification. And in fact, in the textbook, he uses this equality to do a lot more sophisticated analysis, error analysis. So if you are, I'm not going to go through this, but if you are interested, then you can have a look at Lemma's 6.26 and 6.27 and the theorem 6.28. And I personally found the reading, because theorem 6.28 is involved lots of calculation. Possibly some of the calculations are not quite right in the textbook, so there may be some mistakes. But but I found that looking at the 6.26 and then understanding its proof, I found it's quite useful to understand what's really going on. But you don't have to. Just in case you are interested. Okay, so that's the first topic, and then let me move to the next topic. Right. So the next topic that I want to talk about is negative definite symmetry. So what's the motivation behind this? The motivation is that, if you remember, we talked about this many times, the RBF corners. RBF corner have this form. So K of X prime is exponentiation of minus 2 sigma square X and X prime square. So you may ask, is there any way of defining, generalizing this construction a little bit? So here the way we showed RBF corner is the PDS corner is to see many constructions on the PDS corners like additions and the multiplications and limits and so on, or polynomials, the power series, and then normalization. But another way of understanding what's going on in the RBF corner is just like what I explained to you before in terms of the distance. So what's really doing is we try to compute the how two things are related by computing the distance between the two, and computing the distance between the two, and then taking essentially if the distance is very large, the corner will have a very small value. If distance is very small, corner will have a large value. Okay, so by just taking the exponentiation. So then the question becomes, can we somehow find some general binary function which have this type of property? And then this negative definite symmetric corner is the one that that give us way to generalize the construction in RBF corner. So what are we gonna do? So here's our goal. So we'll define. We say that there's a kernels which is just binary function. But we will define some property called this is called NDS. Define called NDS. So this is different from the PDS. So this is a bit like a dual negative definite symmetry. We define this NDS and then show that our goal is so to define come up with the right notion of NDS. And then once we come up with this notion of NDS, we will show the if we will not actually show, I'll just state that the property which said if K, this is a property of the kernel, K is NDS, if and only if exponentiations of minus GK is PDS for all t greater than or equal to 0. So that mirrors the construction on the RBF corner. In the RBF corners, something corresponding to T is, this guy, 2 sigma, that correspond to T. And then something correspond to, say, just using K, that is exactly this distance, the squared distance between X and X prime. And so what the result tells us is that now if we want to mimic the construction used in the RBF kernels works in the sense that it produced the PDS kernel precisely when its parameter K satisfies this NDS property. Okay, so that's the kind of from the perspective of the goal, our goal is to find this notion of NDS such that this if and only if it works out. So what is going to be the answer for this goal or this question? It is the following. So it's a definition. We say that a kernel K is NDS, meaning negative, definite, and symmetry. If and only if the following thing is true, the first, it has to be symmetric. But second, for all x1 to xm in input and or the c1 up to cm real number. Okay, so far very similar to the positive definite property, but here's some difference. So if summation of ci is equal to 0, so then the things that you see before ci, cj, xi, so xi and xj becomes negative. So this is the key difference. It becomes negative, and then but we are only requiring when there's a summation of ci is equal to 0. So that's the definition of negative definite symmetry. And I think one way to understand this definition is to look at one example. A typical example is a distance. So let's define K of x prime as square the distance. Actually, not distance square the distance. Define like this. Then we may ask, is the K going to be NDS? So then this is obviously symmetric. So we don't have to worry about the symmetry requirement, but the more difficult part is it going to be negative definite? And that's something we need to check. So to check this, we will consider x1 to xm and c1 to cm such that this ci's sum to 0. So, and then we compute this quantity, summation of ij 1 to m k ci cj in the products k of xi xj. So we compute this quantity, but then this is the same as xi minus xj square. But that is also the same as xi square minus 2 in the products of xi and xj and xj square. So using this identity, we unroll this unpack, some distribute this sum, and we organize it in an appropriate way. Here's what you will get. We have a I, so all the index goes from 1 to m. So we have ci xi square, but there's a sum cj minus summation of ij ci cj, so 2 times xi xj. Then there's another sum, which is now from cj to xj square, a sum of cr. And at this point, we know that because these sums are equal to 0, so we know this term will disappear. So now we only have this minus 2. So only this term will survive. But now see that this term is has to be smaller than or equal to 0 because of positive definiteness of the inner products, or you can kind of view this directly. Okay. Understand this directly by saying, oh, this is actually minus 2 times summation of I to m ci xi squared. So the norm squared is always greater than or equal to 0, so that is always smaller than or equal to 0. So that's how you can prove that this k is a negative definite symmetry. But but in this calculation, although it's useful, the one thing that you can see from this calculation is the rule that this sum is equal to 0 plays. It say that essentially what it helps us is that whenever we have a terms that only involves the only one side of the kernel, so such as this first part and the last part, which does not really make xi, xj interact, it just talk about only one side, then those terms just disappears because of this, the condition 0. So it only let us focus on the case where xi and xj interact by in this case inner products. Okay, so then that's an example. Then what can we do? Okay, so here's some theorem. So in the book. So here are 3 theorems in the book that I want to talk about. Okay. So the first theorem is a bit technical, but it's 6. But it say that if you have a negative definite symmetric corners, there is a way to construct positive definite symmetric corner. So it's a construction of PDS corner out of NDS corner. It's not in this by doing this exponentiation, but something else. Something else which is a bit simpler. So if suppose we pick some input in X, and suppose that K is a kernel, and K is a symmetry. So in this case, now what we're gonna do is we will define K prime. It's a binary function, it's a kernel, it's a binary function on X using K. Okay, how we define K prime, that this K prime is defined by K of X comma X0 plus K of X prime comma X0 minus K of X and X prime minus K of X0 and X2. So if you, so really, the key part of this definition of kernels and PDS kernels, NDS kernels, the key part is to measure how two inputs are related, right? So really the most important part is this bit. The others are a bit like a normalizations of two inputs. And then really, although it's not exactly of the form, really the K prime is obtained by taking minus of the NDS kernels with some certain normalization. If we do so, then the following is true. K prime is plus PDS if and only if K is NDS. So roughly speaking, if you define the K prime by just putting some minus and then normalize it, then K prime becomes PDS precisely when this original K is negative definite symmetry. Okay, so that's the one theorem. And then the reason, actually the theorem comes with a proof, but I want to talk about the consequences of this theorem because that's something more important. Theorem 6.17 is a consequence of this theorem, which we may be able to actually see. We say the following: K is the same as a kernel and symmetry. So if that is the case, so then K is NDS if and only if exponentiation of minus dk is PDS or P. So that's a theorem 6.17. And theorem 6. So this gives an answer. Like PDS is the one, the NDS is the one that we are looking for. But the theorem 6.18 now say some other things. You say, okay, if you do up to now, then you may say, okay, NDS is great. Then, but it looks a bit like NDS should behave a bit like a square distance. Is it really the case? And the theorem 6.18 say actually that is the case. So if K is X R, and then we are saying K is NDS. So then there exists a Hilbert space. and a feature map such that the k of x and x prime be understood as a squared distance in this Hilbert space. Okay, so this feature map is from x to Hilbert space. So actually, there will be one more conditions. So normalization conditions, which say k of xx is equal to 0 for x. So in order for it to be a distance, I mean, the distance from x to itself should be 0. So if this extra condition is true, then we can actually understand as a k in terms of the squared distance. So these are the results. So the theorem 6.17 is in a sense the why we started to look at this NDS from the in the beginning. Okay, so if say NDS is the right things that we are looking for. Theorem 6.18 say by the way, NDS is really defining the the squared distance in some Hilbert space. Just like we said that PDS kernels is really defining inner product in a very rich feature space. This NDS kernels are really define squared distance in a very rich feature space. So we have about 6 minutes. So I want to give you some idea about how to do the proof. The proof of theorem 6.16, you can do it. Just by using the definition. Textbook has a proof. It requires some calculation, but it's not difficult. If you just do the calculation, if you just sit down, for instance, if you have a exam questions, where I ask you to prove theorem 6.16, if you understand definition of PDS and NDS, you will eventually solve that exam question. Even though that may take some time. Okay? So it's not a hard question. A bit more interesting thing is that how 6.16 implied 6.17 and 18. And let's only look at so let's look at 6.18 first. So let me tell you the sketch. So why theorem 6.18 holds? Okay. The reason is, by 6.16, is because of the So that's because the k prime in 6.16 is a PDS kernel. So by theorem 6.16, k prime there is PDS. So if we PDS, we know that there is an associated Hilbert space. So we can now think about, so let H prime and B prime be the RKHS of k prime and its feature map. So if we do so, then we can now think about maybe using this H prime and B prime, we can construct this corresponding H and B. And it turns out that is always, that is the case. Okay. So how to do this? So it turns out we can just use set H to be the same as H prime. And then if you set B to be the same as 1 over square root 2 B. So then if we do so, then if you compute k and x So then it computes the v of x minus v of x prime square in this Hilbert space. So then this can be simplified, and eventually you can show that, you can use the equality of k prime here, and then also the fact that this, the h prime is an RKHS of k prime. By using this, you can eventually show this is the same as k of x and x prime. So it requires some calculation, but the key idea is to use RKHS of k prime and its feature map, and then really this negative, the NDS kernel, that the k is really computing squared distance in the Hilbert space H, modular some a little bit adjusted feature map, which is adjusted by 1 over square root, 1 over square root of 2. The proof of 6.17, I don't quite right. So yes, for proof of 6.17, again use the I didn't really prove the entire things, but the textbooks say there's an exercise that will help you to solve 6.17. But I want to just point out, if you want, it's an interesting direction for us, for the person who want to construct a new corner, this is an interesting direction. So then but we can also use the theorem 6.16. Okay, so what we do know. So here for using theorem 6.16, in theorem 6.16, I said the most important part is k, that something that these two guys interact with each other. So if you move in this term if you swap in this term and the term that I just highlighted, then you can get the following expression. So say we have exponentiation. So exponentiations of t minus t and k prime, x and x prime. So then this becomes exponentiation of, because it's the k prime and k essentially have the minus relationship. If we just sign changes, we get a t of k, x and x prime, and a bunch of other terms using k prime, but it's not talking about the x and x prime at the same time. When you talk about either x or x prime or x0. Say something like this. So then one thing we know is this exponentiation. So if you split them out, then this becomes exponentiation of tk x and x prime, followed by some function on using x, some other functions using x prime. Goes like this. Okay, so now we are in a very good shape. That's because we know that if they actually this is, I was wrong. So this, okay, sorry about this. So k is the original one, k prime is the new one, k prime. So one thing we know is for corners, if you take its exponentiations, essentially because it's a power series, the K prime exponentiation of PDS kernel is a kernel. So this part is a kernel. And the other part, f of x and f of x prime is really an inner product. Then, but now we are multiplying two kernels together, so that's also going to be a PDS kernel. So showing one directions is not so difficult once you use theorem 6.16. Okay, so that's it for today, and sorry again about overrunning it. And then I'm gonna stay here for about 5 more minutes. So if you have any questions, you can ask me. Okay, so thank you very much.